Hello and welcome to this third unit in this course on the essential maths for AI. Today we're going to be talking about probability theory, and this is again presented by Onyx. This particular lecture is only going to be a brief introduction to probability theory, what it is and how it gets used and why it gets used in artificial intelligence, as well as some of the different types of probability. So probability theory is really the last thing that we need to start understanding the math behind these AI systems. We've covered the linear algebra, we've talked about the multivariate calculus. Now it's time to get into uncertainty. And because of uncertain events, we use probability theory. But before we get started with that, let's just go into a quick overview of what we are going to be covering in this unit. This is video 1. We're going to be just talking about an introduction to probability theory. We're then going to move on to probability distributions. And this is the bread and butter of probability theory that gets applied to AI systems. With that, we're going to go on in the third video to talk about variance and expectation, as well as we'll touch on covariance and covariance matrix. And then we'll conclude by talking about special random variables. So these are going to be some different probability distributions and random variables that you're going to see frequently throughout machine learning papers and AI applications. So a shorter unit than we've talked about in the past. We're really just going over the essentials and some of the main theories, not exactly diving into the nitty-gritty. Probability theory is a very broad area of math, and you could study it for a very long time. We want to focus on what is truly essential to gaining a basic understanding of the math behind machine learning. So let's go ahead and get started with that. So why probability theory? Well, probability theory is a mathematical framework for representing uncertain statements. Or you could also say probability theory provides a means of quantifying uncertainty. It also provides axioms for deriving new uncertain statements. So these two aspects of probability theory are the reasons that it comes up in artificial intelligence applications. So when we apply this to AI, in artificial intelligence applications, we use probability theory in two major ways. First, the laws of probability are going to tell us how AI systems should reason. So we design our algorithms to compute or approximate various expressions derived using probability theory. Also, we can use probability and statistics to theoretically analyze the behavior of proposed AI systems. So probability theory is a fundamental tool of many disciplines of science and engineering. In a statement, probability theory allows us to make uncertain statements and to reason. So, as you can see from this brief overview, why probability theory is so important to artificial intelligence. Handling uncertain cases, because this is really what humans do. We analyze information, everything's not always certain, and then we make a decision anyways. So how do we reason through that process? How do we look at some events that aren't black and white, or they aren't cut in stone, and then make decisions anyways? So computer systems, which are usually even in AI systems, they're working in ones and zeros. That's about as black as white as it can get. But when you get enough of those and you build them into these machine learning networks or neural networks, different deep learning applications, you're faced with a lot of uncertainty. And so how do computer systems handle that, reason in the presence of that uncertainty, and make decisions in the face of that uncertainty? So why is there so much uncertainty in machine learning? Well, that can primarily be broken down into three reasons. The first being inherent stochasticity in the system being modeled. So in a lot of different cases, even if we built a perfect model, everything was set up exactly as it is in the real world, there would still be some uncertainty. An example of that could be a model of quantum mechanics. So quantum mechanics is built upon the fact that subatomic particles behave in a probabilistic nature. So there's some inherent uncertainty in the actual underlying quantum mechanics. So even if we had a perfect model, there would still be uncertainty in our overarching model that we create. The second reason that we could have uncertainty is because of an incomplete observability. And this, I would say, is the primary source of uncertainty in artificial intelligence. We do not have or cannot observe all the variables that drive the system. If you think about machine learning in general, oftentimes we get, maybe, let's say we're doing a computer vision application, we have 1,000 example images. And these 1,000 example images are supposed to be representative of the entire possible sample or distribution of images out there. So that would be an example of not having all of the variables. And this comes up all the time. You know, when you have labeled data that you're training systems on, if you're doing supervised learning, you're not going to have all the data. That's why we need to build models that generalize well. If you're building artificial intelligence systems that rely on reinforcement learning, we might not be able to know all the variables that drive the system. We potentially couldn't know all the different game states, all the directions that a robot could turn in a room. Different reasons that we could or could not have all of the variables that drive the system. Another example of that could be economic models. Maybe we're trying to predict economic models, and even society as a whole really doesn't understand entirely what drives the stock market up and down, so it would be impossible to feed one of these networks all of the relevant data points to predict, let's say, the stock market. So an economic model could be an example of incomplete observability. And once again, I would say this is arguably the primary source of uncertainty in artificial intelligence applications. Finally, we could have incomplete modeling. Let's just say that we use a model that discards some observed information. We could do this for a variety of different reasons. An example might be that we build a simplified model of the brain simply because we don't have the computational resources to simulate all 2 billion plus neurons in the human brain. So we might kind of dumb it down a little bit and build a simpler model. So we're discarding some of the observed information. And another example of that might be, let's say we're trying to do something with space and we discard the gravitational effects of every planet and star outside of our solar system. So a lot of the times we might have information and choose not to feed it into our networks simply because of computational limitations or other reasons. We are going to have incomplete modeling, and this is another source of uncertainty. So we don't use all the observed information, and as a result we have some uncertainty or some probability theory that needs to be applied to this network. So here we go, 3 main sources of uncertainty in artificial intelligence systems, and because of these 3 reasons we need probability theory. Next, let's talk about some types of probability. The first being what you would probably thought of first, and this is frequentist probability. This is exactly what comes to mind for most people when you hear probability in the first place. It's just the frequency of events. So an example would be the chance of drawing a certain hand in poker or another game like that. The chance that something happens, the chance that you get a jack and a king in blackjack. The frequency of events, this is going to be called frequentist probability. On the flip side of this, we have the lesser thought about Bayesian probability. And Bayesian probability is more like a belief, and this actually comes up in artificial intelligence a lot. How confident are you? It's a degree of belief. An example of this would be a doctor saying a patient has a 40% chance of having the flu. So this doctor is basically saying, I'm about 40% confident that this patient has the flu. It's not that the patient, the patient either has the flu or doesn't have the flu, so there's not a 40% chance of him having the flu with his particular conditions, because he either has the virus or he doesn't. In another example of that, in going back to the poker, after you've already been dealt a hand, you could say that another player at the table would be operating with a degree of belief if he was trying to predict your hand. You could say, I think the other player has about a 20% chance of having this particular hand. Since the hand's already been dealt, we're now dealing with Bayesian probability. It's a degree of belief. And so in probability theory, these actually get treated very similarly. And the only way to satisfy common sense properties about probability is to treat Bayesian probabilities as behaving exactly the same as frequentist probabilities. The same axioms control both kinds of probability. So while it is subdivided into these two types of probability, we are going to treat them and model them exactly the same way in our systems. And that'll actually come up a little bit more when we're talking about variance and expectations and diving into probability distributions in the next couple of lectures. All right, so that's just a brief introduction to what we're going to be talking about in this unit. This is probability theory, an introduction to probability theory in this particular lecture. Moving on, in the second video, we are going to be talking about probability distributions. So we'll actually get to move on from the theory a little bit and dive into some of the math. Thank you very much for listening.